All right, let's dive into this stack of quantum computing articles and notes you've got. We'll pull out the good stuff. Make you the life of the party.
Right. It's fascinating stuff.
Yeah, it really is.
What's so interesting here is how your sources, they all highlight this intersection of physics and computer science, don't they? Like, we're really talking about harnessing the strangeness of the quantum world for, well, practical use.
Exactly. And Hidary's book, Quantum Computing, An Applied Approach, that's a really good place to start, I think, because he just jumps right into this idea of superposition, which is kind of the bedrock of all this quantum computing stuff. And honestly, when I first read about it, I was like, what is going on? Like, can you imagine something being in two states at once?
It does seem impossible, doesn't it?
Really?
Based on, our everyday experience. But Hidary, he uses this really good example of polarized light passing through filters.
Mm.
And like in the quantum world, a single photon can somehow pass through two filters that should block it. It's as if it's taking both paths at the same time. And that's kind of the beauty of superposition.
Okay, so it's like a qubit can be both a 0 and a 1 at the same time.
Yeah.
But then it gets even weirder with entanglement, right? Look, this is where Hidary's description of superposition on steroids really clicks.
Oh, he's not kidding, is he?
No.
Entanglement is this wild phenomenon where two qubits are linked and their fates are totally intertwined, even if they're like light years apart. It's crazy.
Yeah.
Einstein really struggled with this concept. He even called it spooky action at a distance.
Kooky is right. Like
Yeah.
they're communicating instantly, breaking all the rules.
I-
But before we go too far down the rabbit hole, Hidary mentions this thing called Max Born's rule. This feels like our anchor back to reality. Can you explain how that works?
Yeah, absolutely. Born's rule basically says that while we can't know for sure what state a qubit will be in when we measure it, we can calculate the probability of it being a 0 or a 1. So think of it like flipping a coin. You can't predict a single flip, right? But over many flips, you can work out the probability of getting heads or tails.
Okay.
It's the same kind of idea.
So even though the quantum world seems inherently random, we can still work with it mathematically.
Exactly.
And this probabilistic nature, this is what's so exciting because it underpins some of the the coolest potential applications of quantum computers, like, teleportation or super dense coding, right?
Absolutely, yeah. And your sources even touch on like the history of this probabilistic interpretation. And it was a really hot debate in the early days of quantum mechanics, which just shows how revolutionary these ideas were and still are.
It's amazing to me that they were thinking about this stuff so long ago, and we're just now starting to see it come to fruition.
Incredible, isn't it?
Yeah, it's mind-blowing. So, okay, we've got these mind-bending concepts kind of like somewhat, a grasp on, but how do we go from these theories to actually building a quantum computer? Because one of your sources actually provides like a checklist for evaluating a quantum computer. It's called the DiVincenzo criteria, and it seems like a pretty high bar to clear.
Oh, it is a high bar. And it basically outlines the essential things a system needs to be able to do to be considered a true quantum computer. Things like, we need to be able to isolate individual qubits, control their states really precisely, and make sure that they can hold information long enough to be useful for computation, which is harder than it sounds.
Oh, I bet. And to make things even more interesting, it seems like there's not just one way to build these things. You know what I mean? Your sources mention several different physical implementations, each with its own pros and cons. It's like choosing the right tool from a quantum toolbox, isn't it?
And that's a great way to put it.
So it's like we've got all these different quantum construction crews,
Yeah.
right? Using totally different materials, but trying to build the same thing.
Yeah.
A quantum computer that can actually do something useful. And some of your sources were talking about superconducting qubits, trapped ions, neutral atoms. Like, how do you even choose which direction to go? It's like the quantum version of deciding between, I don't know, wood, brick, or steel for your dream house.
That's a good analogy. And, just like with house materials, each approach has its strengths and it has its weaknesses. Superconducting qubits, for instance, are built using these circuits, but they have to be cooled to incredibly low temperatures, like almost to absolute zero, which is mind-boggling.
Wow, that's cold.
Yeah, think of them as like tiny racing circuits, but for electrons, where the flow of current can be manipulated to represent those zeros and ones.
Huh. It kind of reminds me of how, like, classical computers used to take up, like, entire rooms with those massive vacuum tubes.
Oh, yeah, absolutely.
We've come a long way, haven't we?
We have, but what's funny is there are still parallels, right?
Yeah.
Because just like those early computers, current quantum computers, They're so sensitive to their environment.
Yeah.
And remember decoherence, that thing we talked about,
Yeah.
where qubits lose their quantum properties? Well, that's a major hurdle for these superconducting qubits.
Right, like trying to write with disappearing ink.
Exactly.
Not very useful. But regardless of which building blocks they choose to work with, right, your sources all seem to agree on one thing. A true quantum computer has to be universal. And I feel like we kind of glossed over that word, but what does that actually mean? One of the articles you gave me even tied it back to the Turing machine, which seems so long ago in computer science time.
Right. Ancient history. But it's such a brilliant connection, honestly, because the Turing machine, it's a theoretical model of computation. And it showed us that you can have a single machine that could theoretically compute anything that's computable. And in a similar way, a universal quantum computer would be able to simulate any physical process, which, I mean, the possibilities there are just wow.
So we're talking about like simulating complex molecules to design life-saving drugs, or like understanding the fundamental properties of materials to create entirely new ones.
Exactly.
Yeah.
Just imagine a future where we can design personalized medicine tailored to your unique genetic makeup. Or we can create super efficient solar cells that like solve our energy crisis. That's the promise of a universal quantum computer.
Yeah.
It's incredible.
Okay, so that future sounds amazing, but let's be real for a second. We're not quite there yet. And your sources do a good job of highlighting the limitations that we're facing. We've talked about decoherence, right? But there's also the issue of scalability, right? Like, how do we actually build these systems with enough qubits to tackle these really complex problems?
That is the million-dollar question, or, well, maybe the billion-dollar question.
Right.
Because right now we're still in the early stages of just trying to build quantum computers with enough stable qubits to really outperform classical computers, those practical tasks that we've been talking about.
So it's like trying to build a super fast car when you can only manufacture like a handful of functioning wheels at a time.
That is a very good analogy.
Okay, good. I'm glad one of us is good at analogies.
Well, you're doing great.
But it's not just about the hardware, is it? It's like, even if we had this quantum computer with millions of qubits today, we'd still need the right software, the right instructions to actually unlock that potential.
Oh, absolutely. And that's where these quantum algorithms come into play. They're like sets of instructions specifically designed to leverage all of that, the power of superposition, the entanglement, all of that.
So like giving the right directions to our quantum supercar?
Exactly.
Okay, good. And thankfully, your sources provide a few roadmaps, right? We've got like Shor's algorithm and we've got Grover's algorithm. Those are like two of the classics, right?
Yeah, they're the big ones. And they really show us what's possible with quantum algorithms. Shor's algorithm, for example, has really kind of thrown a wrench into the world of cryptography.
Yeah, because it could potentially break the encryption methods that we rely on every single day.
Yeah, exactly.
I mean, that sounds like a plot from a spy movie.
Right. And it really underscores the real-world impact of these algorithms, because Shor's algorithm could theoretically factor large numbers exponentially faster than any classical algorithm. And that's a huge deal, because factoring large numbers, that's the basis of many encryption methods that are used everywhere to secure communications online, financial transactions, even government secrets.
Okay, so that's what I'm talking about, like deep dive consequences, right? That's huge. But what about Grover's algorithm? That one seems, I don't know, maybe a little less world-shaking, like more about like finding a needle in a haystack, but like more efficiently.
Yeah, that's a good way to think about it. Imagine you have a phone book,
Okay.
and it's got 1 billion names in it.
Got it.
And you need to find one specific person.
Yeah.
Grover's algorithm can give you what's called a quadratic speedup for this kind of unstructured search problem, meaning it could find what you're looking for much, much faster than any classical algorithm.
Okay, yeah, see, that's what I was getting at. That's still a big deal, right? Like that could be huge for things like database searches. And I mean, you already mentioned drug discovery, even just like optimizing complex systems. It's not just about speed, right? It's about like unlocking possibilities that just weren't even like on the table before. So we've got these amazing algorithms, right? Like Shor's and Grover's. They can like revolutionize everything from cryptography to like the way we discover new drugs. I mean, it feels like we're like right on the edge of something massive. But there's this other thing that keeps coming up in these articles you gave me, this idea of quantum supremacy. What does that even mean? And why is it such a big deal?
So quantum supremacy, think of it as the ultimate test for a quantum computer. It's that point where a quantum computer can solve a problem that would take a classical computer, even the most powerful one we have, an insanely long time. Like, we're talking, even with all the computing power in the world, it's just not practical. So it's really about proving, like definitively, that quantum computers can do things that classical computers just, they can't.
So it's not even just about speed at that point. It's about doing things that are impossible for a classical computer to even attempt.
Exactly. And actually, one of your sources mentioned this experiment that Google did with random circuit sampling. And that was a big deal because it was seen as evidence of quantum supremacy. Basically, they show that their quantum computer could do this one specific task in minutes when it would have taken a classical supercomputer thousands of years to do the same thing.
See, that's what I'm talking about. That's huge. I mean, that really shows you what this technology could do. But even with, these mind-blowing algorithms and proving quantum supremacy, there's still that one big thing, right? Error correction. Like, how do we keep these qubits from losing information? It seems like a constant uphill battle.
Oh, it definitely is a challenge. Error correction is essential. I mean, remember that analogy we were using about qubits being like disappearing ink?
Yeah.
Well, imagine trying to write an entire book with disappearing ink. You would need some really good error correction to make sure the message actually came through.
That's a good point. And Hidary, one of your sources, he uses this analogy of like a 3-qubit repetition code, right? It's like having like a backup for your backup. So if one qubit fails, you can kind of use the other two to figure out what it was supposed to be.
Yeah, that's the basic idea. It's like a simplified way to think about it.
Yeah.
You're spreading the information across multiple qubits, so even if some of them get messed up, you can still get that original information back.
Okay, that makes sense. But from what I'm reading here in these other articles, it seems like error correction in a real quantum computer, it's way more complicated than just having a few backup qubits, isn't it?
Oh, for sure. We have to think about all sorts of errors that can happen in these quantum systems. There are bit flip errors, where a 0 might flip to a 1, but then there are these things called phase flip errors, which are even weirder because they're unique to the quantum world. It has to do with the way qubits act like waves. And the worst part, these errors, they can combine, and they can spread through the entire system. It gets very complex very quickly.
So it's not just about fixing individual errors. It's like you need to design the whole system to be resilient to errors. So even when things go wrong, and they will, it can keep working. That just seems like such a difficult thing to do.
Oh, it is a huge challenge.
Yeah.
But researchers are working on it, and they're making progress. They're developing all these incredibly sophisticated error correction techniques and codes. And one area of research that your sources mentioned is called the stabilizer formalism, which sounds very intimidating.
Yeah, that one, even for this deep dive, I was like, whoa, okay. Do we need to, unpack that one?
I don't think we need to get into the nitty-gritty details right now. Just know that it's basically a powerful mathematical framework that helps us understand and design these really complex error correction codes. Like, imagine it's a special language that quantum physicists use to talk about and manipulate these crazy quantum states.
Okay, that makes me feel a little better knowing that, there's people way smarter than me working on that. But honestly, after reading all of this stuff, I have to say, I'm feeling both excited and a little overwhelmed. It's so clear that quantum computing has the potential to just completely change the world, but there are still so many things we don't know, and it just seems like there's a really long way to go.
No, I think that's totally fair. Quantum computing is this constantly moving target. You know what I mean? There are new breakthroughs happening all the time. The important thing is that you're starting to grasp the basics. You understand the challenges and the incredible opportunities, and that's what matters.
You know what really blew my mind, though? Reading about these dequantized algorithms in Hidary's book, it's like the quantum world is already impacting the way we do classical computing even before we have these fully functional quantum computers.
It's wild, isn't it? It really shows you how just the pursuit of quantum computing is pushing the boundaries of how we understand computation itself. Like these dequantized algorithms, they're classical algorithms, but they're inspired by quantum techniques. So we're already seeing that exchange of ideas.
So it's like, even if we never figure out how to build this large-scale, perfect quantum computer, just try and get there is already making our classical computers better.
Yes.
Wow. Well, you've definitely given me a lot to think about. And for everyone listening, remember, the future is quantum, but it's up to all of us to, figure out what that actually means. So keep asking those questions, keep exploring, and who knows? Maybe one of you listening will be the one that unlocks the true potential of this amazing technology. Till next time, happy diving.